So I first like to thank the organizer to have included this Julia session in this PyHEP 2021 editions, and to have give me the opportunity to give one of these two talk of this session. So first, introductions that have Jan showed experience. Julia is a new programming language, and actually is even new, quite new for me, because I discovered it while I was making a survey for programming language for the QP experiment, so not really double beta decay experiments. So this was just in this started in last April. So the idea was to know which language we should use for this coming experiment. And so it's new for me, so I'm not biased by use of the language, and I also actually learn it by preparing this talk. And this was as fast as learning Python, and maybe even faster because there was a lot of similarities. So I will present Julia to you in the perspective for using it for HEP application, and more particularly for LHC. So, sorry, yes. I try to avoid the scrolling, but okay. So first, the context. In HEP, and especially for LHC, high performance computing is central. So here you have the needs for CML, and similar for the other experiment of LHC, the current need and the projection for HLHC. So on the left is the CPU, on the right is the data storage. So it gives also an idea of the size of data that we are processing. On the left, the unit is a tera CPU times seconds. And you see that in 2027, we reach 1,600 tera CPU seconds. And this corresponds to nowadays CPU with 10 cores. So computing plays a role in the theoretic prediction, so the simulation of the proton-proton collisions, in the simulation of the detector response. So these two appears as the MC on the left plot, in the reconstruction of the physics events that appear in the prompt data and non-prompt data, and the most of the data that are on the right, everything except the user. And the analysis, and then the final step is the analysis of the reconstructed events, so that we call physics analysis. And what we should notice here, and what is very important, is that this analysis part is a substantial part of the CPU that we are using. So the analysis of events, of physics analysis, behind each result publication, each publication of the experiments, of LHC experiments, we have tens of thousands of computing jobs that have been run on the worldwide computing grids. And we are publishing thousands of papers. Last summer, both ATAS and CMS celebrate their respective anniversary of their respective 1,000th paper. So C++ is widely used, and its performance that just far is essential. The research, the code that we are writing here is a research code. So this is developed by the main authors of the prepared publication. This is a physicist. And so Python is attractive actually because it is fast writing of code and fast writing of code, and it's especially important for code that is just done for publications, and also for the library ecosystem that goes with it, and especially for machine learning. But it does not meet the performance that is provided by C++. So how we deal with it, that we actually used in conjunction C++, and there was a huge development that underway, and this is thanks to many people from HSF to leverage the performance of Python. And always the principle is to move the critical part in the compiled part. So, but the more attractive things will be to have a programming language, is what I thought before learning Julia, that offer both pros of C++ and the pros of Python. So high performance code and fast writing code. So this, as you will learn before in the previous talk, this is already on the market. This is Julia. So Julia is solving this two language problem. So this is actually not specific to HEP. I think is in the many research domain, and this is people from a statistics domain that solve it. So in 2009, they had a quite ambitious idea of developing a language that would do both fast and easy coding and fast running. And in 2013, it comes out Julia. So the birth of Julia was there is a 0.1. So this is really a breakthrough, and it's really recognized by different awards that I put it here. So since these conceptualizations, there was 12 years that passed, and a lot of developments that have been done. And since these 12 years, and also 5 years, in 2016, as no, I think HEP I considered Julia. So since these last 5 years, there was a lot of things that have been done, and Julia has improved a lot, and from release to release. And they also aggregated many package developers, and we'll see that in the next. So for Julia, so you see, it can be used for HEP, and Jan has published a paper recently with Marcel Saniski on the performance of Julia for HEP. So actually nowadays, Julia is a mature language with a wide ecosystem, and what I will show today. So I want to make some parentheses on loops. So you will, I think you will know why we come to with looking at these pictures. So HEP data analysis is a looping game. What we do, I mean, we are looping on billions of LHC events, and for each event, we are looping on tens of hundreds of objects, which are particles or particle candidates. And in the events, what we do often, we do matching and particle matching, clustering, jet clustering that Jan discussed, combinations, which means that for each object, we again do loops on the order of 10 of hundreds of objects. Actually, these outer loops hide several loops because there are so many events that are spread in several files, and we have different data sets. So they correspond to simulation data with different trigger streams and different physics events. And this loop of loops is actually repeated several times for each analysis, because the process that you do the analysis, you look at the results, then you improve the analysis, you look at the results again and again until the publications, and this process can take several years. So actually a line of code is executed billions of times, even for cleanest code that was just developed for publications. So why I'm discussing about loops is because Python dislikes loops, contrary to the snakes that we have seen on the picture. So a master rule for high performance computing in Python is to avoid writing loop. So how we do this is that actually we push the loop down to underlying compiled libraries. This is the approach of the NumPy vectorization. So in such way that the loop is done in compiled code and high performance codes. But the code that we have to run here for the analysis is a code that we develop for the searchers. It's not a common code that we can use from a library which has already done. So let's make a small test for a loop. So let's loop in Python. So here I define a simple function. So I just want to compute the sum of the 1/n series. So I define the functions, then time it, and it takes 120 milliseconds. So it took that 19 milliseconds yesterday. Okay. So is it fast? Is it slow? We have to compare with C++. So let's we just remain at Python is order of 100 milliseconds. So here's I implemented in C++. Sorry, I should not spoil too much. So here's the code is similar. So we have a get time of day is just to time the code, and here you have the loop that you see here. I don't know if do you see my pointer?
Yeah.
Okay, right. So since it's compiled, you need to compile it. I compile it with two options, with default option of GCC and with the maximum optimization, which is -03, which makes sometimes more difficult to debug when you run the debugger. And what do we get? Is it runs 5 milliseconds. So I probably zoom. It is slowing down my computer. So for 5 milliseconds for without optimizations and 2 milliseconds with optimizations. So we keep what we remind from here, the output of it is that it takes 60 times faster with C++. So now, how is it going with Julia? So here's the Julia code. So now you see how Julia code looks like. So you can see it's similar to Python. So you have different functions. So is the accumulator. So a few difference. You don't need the colon at the end of the for loop or if loop. You don't demand indentation, so no more bugs because you deleted an ident or you added one. But it's still, I mean, it's still as compact as a Python, because anyways, the line with the ends you need in a Python. I mean, you will put in anti-line in Python if you format properly your code. And also there is like in Python, you have many sugar. Is it how you say sugary or sweets in the language? And you see that here we have the underscore that makes it easier to read the large numbers. So let's just run it and time it. And here it took 1.7 milliseconds. So I know this by chance is even faster than C++, but when I did the test, it was similar. So actually, sorry for the small fonts. So it took 90 milliseconds for Python and 60 times less for Julia, and this Julia is the same performance C++. So now performance is not the only thing, because we want also to have is programming. So what you have seen before, we already seen that the syntax is similar to Python, and so we don't have any more std map, std vector, and you don't have the compiling step either. So another thing which is important is the programming nowadays is a community. So it's easier to program in a language where you have a large community that is using it. Why? Because what we are doing nowadays, what I'm calling Google programming. So it's when you don't know how to do something, you just go in your preferred search engine, mine is the Go, and you type something, you type what you want, and you will find how to do it in Stack Overflow. So this we can try it. Maybe, yeah. So I don't know what I want to do. If Julia, if I want to search a string, search in a string. And you see, you have many things. Strings in Julia. Yeah. Okay, I want this. It's constant. And this, when I learned the Julia for this talk, anything I was looking for, I found it on the internet. So let's come back to the talk. Sorry. So yes, it's open the same. Okay, sorry. I use Surf to have a full screen, but I don't know how to go back. Back is control. Control H. Okay, I did the H and Control H. was supposed to open in a new. Okay, it's fine. So now another. See, I lose time. So another important reason of success of Python is the ecosystem. So I knew before this workshop that there was a large set of library and an active development for that set of library for Julia, and this growing. And in addition, Julia is firstly used by scientific community, so the libraries are oriented to our needs. But during this workshop, I did the following games that anytime someone mentioned a package was using in Python, I type in the DodaGo the name of the package and Julia, and I was amazed by the results of this game. So this is here. So this is all the package that was mentioned, and the check mark means that there is a package in Julia, and the cross there is no package. So there's only two. There is a FreeCAD, which has no binding for Julia. And actually, there is an active discussion among the FreeCAD developers about Julia, and FreeCAD is actually suffering. The developers are suffering of a double language problem, and moving to Julia would actually be a benefit for them. And there is a hypothesis, which is for use for testing code, which is not in Julia. There was one, but is no more maintained. But there was tools to test, as Jan mentioned. So now another important thing that we have analysis the data, so the data format, the support for data format. So for non-HEP, you have many things. For HDF5, for packet, for root, as Jan mentions, there is the uproot and the unroot. So I think we are missing a solid and performance library, and this, if we want to move to Julia, it's probably the first things to address. We have to build the package, we consolidate unroots. So this package was developed by physicists that wanted to use Julia to do the analysis and needed to read the data from the experiments. So when you develop, there are also needs of advanced tools. So maybe I will skip this because I'm running out of time. So, but I know because this is important actually. So there is IDE. So if you have support for Emacs and Vim, and people that are used to more advanced integrated development environments, there is a very nice plugin for Atom, and also for VS Code. And actually, it transforms this IDE as a framework to do analysis, because you have the plots, you can run the code there, and you also a nice debugger. And you have notebooks, or you have a Jupyter. Jan mentioned Ju is for Julia, and you have also a notebook which is called Pluto, which is specific to Julia. It's a new generation notebook where the cells are automatically updated. So in Jupyter, when you modify a cell, if you have to run again manually the cells that depends for which result depend on it. Pluto resolve itself track the dependency, and we just update the cells that depend on the cell that you updated. So there is all the developer tools that needs. As Jan mentioned, there is a good support for package installation. Actually, Python made it easy with Kunda and PIP, and it's even easier with Julia, because you have is part of the language, of the library, the main library. And so everyone is using the same. And in addition, if the user is including a package is missing, it will just give the instruction how to install it. So we can try. If I do import link, I get this message: just run import package. I copy this code and we will install the missing package. Okay, so Julia has also a rep command, so like IPythons, and here's a special mode for the package. So I want to come to another topics with the interoperability that make the. So I will skip this because Jan addressed it. So even better than you must more than me. Actually, I already planned. So I put for reference the way how to call different language from Julia. And now I will go to HEP, to an example of that. So let's use now HEP for on the Julia on the HEP examples. So I used the CMS Damion spectrum analysis on the park data, which has actually used as a sample for many by many of us. So one caveat is you have to keep an extremely simple analysis, and it's way far from a usual LHC analysis. So let's just start and try this. Okay, so this analysis is consistent measuring the Damion spectrum, the Damion mass spectrum, and let's use the data special data that were stored, that we call park data, we stored a reduced, which just stores those objects that we needed to do the analysis. So when we took the data, so the muon was reconstructed online, and this allowed to register more data, and allow us to reach a very low mass in the spectrums. So this also the consequence is also that the data set is quite simple. So you just have the muons. So here you have the information on the spectrum. So on the analysis, sorry, you have the spectrum. Here you see the thick peak, HEP psi, and you have the reference to the paper. So now let's do it on Julia. So this is what you have in the data set. So to do the analysis, we need some tools. So you need to do histogramming. So histogramming in HEP is a bit different than how it is done in other fields. So I mean, it's very simple to do a histogramming package. That's probably why we have so many in Python. And we also need to store for momentum. So this is what I have in another notebook. So we don't need to touch the detail of this. So we need the data file. So this is already downloaded, and then we need to read the data. So this is the function to read the data. So I don't know if I come in detail on this. Probably it's not so. Yes, no. So interesting. I would just go to the analysis. So now let's come to the analysis. So just to say what this function do is that we just read the file fname that we provide. They read it and provide the event that is read, which is actually just muons here, to a function that we pass to it, and we can limit the number of events process. So here is the analysis, the code. So you see, code is very similar to things as the Pythons. You don't need to mention the type. Also, we often mention it when we define the structure, so the classes. And even if you don't mention it, specify the type, the compiler find it and make efficient code. So we define the histograms, and we fill the histograms with the Damion mass that we compute. So we read the event. So here's a special construct which is very nice in Julia. So this do, which actually do something which is used in place of the with construct of Python, but is more powerful. So what it does is actually define anonymous functions or lambda functions, which is what is after the do here, and it just passes these functions to the previous call, so this read. So if you remember the read that I showed before function, take a first argument that is the functions. So what will we pass? So this we don't write it here, and actually the compiler will pass the functions, the lambda functions, which is implemented in this do block. It passes functions, and then it executes this block. So the read will execute this block, and the muons here, we see muons is the parameter of the functions that is passed when the read function is call it. So this is very powerful. So this, and I mean, this allows to make a neat code, because you don't have. If you would do that with a lambda function in C++ or in Python, this code will go inside the parentheses of the read, which make quite a clutter code. So the analysis sample will request exactly 2 muons. So this is the length of the pure muons. The 0x is to be 2, so it will be muons dot size in Python. And we ask to have the muons to have opposite charge. And so is there?
Philippe, you've got 3 minutes left.
Sorry, yes.
Yeah.
And then we just plot we compute the mass and we do the plots. So now, okay, this is what I explained. So now we can run the code, and let's see. I'm just surprised by the. Okay, so it takes 30 seconds. Maybe I should not run it. Okay, so it takes 30 seconds. You can believe me, trust me. So now let's. Oh yeah, but I will need it to make the plot. So maybe I will go to the questions because I have just 4 minutes left. So just to say that we have also, okay, it's done. So we have also many language, and that in addition, what is something nice that we have we have language that provide a common front end for the different language package. So give you an interface, a common interface. So here is the code to make the plots, and you have a nice plot, which is here the diamond spectrum, like we've seen the one from the paper. So that's thing that if you prefer data frame, we could also do on the analysis with data frames, because Julia is also supporting data frame, and these are also the equivalent of Dask, so you can do parallel computing. Okay, so we just go back to the so so anyway, yes, okay. So this was my end of my presentation. So Julia offers the what is this? Oh, I have someone writing. I see something. I don't have anything else. Okay. Can you hear me?
Yeah, I have been hearing.
Okay, so I don't know. I have now black screen.
The slides are gone. Yeah, it's
okay. Anyway, so you have seen the conclusions. So now, I mean, we can go to the questions, then go to the discussions.
Okay.
But can you tell me the questions, because I don't know why I have a black screen. So I mean, okay. Yes, it's back. It's back.
It's back.
Yes. Okay.
Otherwise, I can just share it for you. You see that now?
Yes, I see only 2.
Yeah. I suspect people are waiting for the discussion.
Yes.
So, all right. Okay, please go ahead.
So the first question is what is the underlying difference between Python and Julia? So in terms of usage, Python is much faster, as I show, and in the implementation is that Julia is doing just-in-time compilations, and by natively. It's not so it's a bit similar to the Numba, but it does with everything. And okay, and there is also a nice feature, but okay, of a multi. Okay, but yeah, I mean, there's also the nice feature which is called multi-dispatching. So it's something that extends the object-oriented programations, and that actually allows to reuse much more to reuse code of others. And I mean, actually, the developer of the program of this language were surprised at how much is improved the reusing of code, and it's very easy to improve code to reuse code of others. Actually, so in object-oriented in C++, if you want to extend the library, what you usually need is to ask the authors to change the class, because you need to add function to the class. So in Julia, you don't need. You can just extend the class and add the functionalities. And this makes it code much user. So actually, it brings together the templates, the generic programming, a template, with the object programming. And the also next question was how many? Oh, for the how many events? I don't remember. This is I don't remember the number, but it's a full data set. It's a full data set, so it's this was on the run one Park data set. So to give an idea, so doing it on Python with using a T3 takes 4 hours, 4 hours and 50 minutes. And I think with a data frame and Sklink, it takes something like 20 minutes, I